Hello there, and welcome to this live session of the Chemistry Clinic brought to you by Boost Revision. I'm Dr. Owusu. This evening's session is the delayed session on halogenoalkanes and the nucleophilic substitution mechanism. I do apologise for the technical difficulties we had yesterday. It's all been sorted out, and hopefully we will have a smooth session today. So what are we doing? We're looking at AS chemistry, and we're looking at halogenoalkanes specifically, and the nucleophilic substitution mechanism. And as usual, we will look at some theory, and then we will look at some practice questions. And before we start, I'm going to connect my tablet so that we can have a sense of what we're going to be looking at this evening. So do bear with me for a few seconds while I do that. Okay, so yeah, you should have a copy of the specification on screen, and we're looking at halogenoalkanes or haloalkanes in your specification, and we'll be looking at the substitution reactions that these halogenoalkanes undergo. Of course, to understand the reactions of these halogenoalkanes, we need to know a bit about sort of bonding in the halogenoalkanes, especially the polarity of the carbon-halogen bond. And we'll also be looking at how these bonds are broken in hydrolysis reactions. We'll define what a hydrolysis reaction is. And then towards the middle portion of the session, we will look at how halogenoalkanes can be broken down to give halogen radicals, which have an impact on ozone levels in the atmosphere. And then in the final third, we will look at some practice exam questions on halogenoalkanes and the nucleophilic substitution mechanism. Okay, so to our work on halogenoalkanes then. So on your screen, you should see 3 examples of halogenoalkanes. And if you've done the alcohols topic, then you will know that alcohols can be classified as primary, secondary, or tertiary. The same is true for halogenoalkanes, although the OCRA board doesn't sort of make a big deal of that. You've got a chloroalkane, a bromoalkane, and an iodoalkane on your screens. If I highlight them in yellow, chloro, bromo, and iodo. And as a bit of practice, we should be able to name each of these molecules. And if we consider the first one, the chloroalkane, that should be chloroethane. So no need to number the position of the chloro group because either carbon would be carbon number 1, so we've simply got chloroethane. In the second example, you've got a bromopropane, but it is important this time round that you do say where that bromine atom is. That bromine atom is on carbon number 2, so that would be 2-bromopropane. So 2-bromopropane. And finally, in the third example, we've got an iodo propane, but the iodine atom is not the only substituent. You've got a methyl group present as well. And because we name our substituents in alphabetical order, it has to be 2-iodo before 2-methyl-propane. Okay, so we've got 2-iodo and 2-methyl-propane. Okay, so that's a bit of practice at nomenclature. Make sure that you are, whenever you have the opportunity, sort of attempting to name these organic compounds. Okay, so we've got 3 examples present. Before we can look at the reactions of the halogenoalkanes, it's important to consider polarity in these molecules. Now, because you've got a difference in electronegativity between the carbon and the halogen atom, these bonds are polar. Okay, so worth making a note of that. So you've got polar bonds because of the difference in electronegativity. Okay, so halogen more electronegative than carbon. Okay, so as a result of this difference in electronegativity, you're going to have dipoles on across the carbon-halogen bond, and these will be permanent dipoles. So you've got a delta plus on each of the carbons bonded to halogen, and of course a delta minus on each of the halogens. Okay, so for our 3 examples shown there, we've got a delta plus on the carbon, and at the other end of that bond, the carbon-halogen bond, you've got a delta minus on the halogen atom. Okay, so you've got a polar bond. And because of that delta plus charge, because of that electron deficient carbon atom, these halogenoalkanes are very attractive to nucleophiles. They're very susceptible to nucleophilic attack. Okay, so interactions with nucleophiles, they are sort of attacked by nucleophiles, and we will define what a nucleophile is shortly. So nucleophiles are, of course, defined as electron pair donors. So a bit of a refresher there for you. So electron pair donors. And so we've got polar bonds. You've got electron deficient carbon atoms bonded to our electronegative halogen atoms. And as a result, you're going to get nucleophiles attacking the carbon atom with the delta plus on it. Okay, so let's look at some of the reactions that these halogenoalkanes will undergo. The most common, the first one that you will encounter is hydrolysis of a halogenoalkane. And at this stage, it's worth sort of defining what a hydrolysis is. And you can work this out from the name itself. So the hydro part of hydrolysis refers to water, and lysis refers to breaking a bond or breaking down something or breaking apart something. So a hydrolysis reaction is using a water molecule to break a covalent bond. Okay, so in this instance, the covalent bond we're talking about is, of course, the carbon-halogen bond. And I've represented the halogens with the letter X, which is the universally accepted sort of symbol for the halogen. So we're looking at carbon-halogen bonds, looking at CX bond. And there are some interesting trends that you can sort of observe with the different carbon-halogen bonds. And there is a distinct sort of difference in the rate of hydrolysis depending on whether you've got a carbon-chlorine bond or a carbon-bromine bond or a carbon-iodine bond. And the red arrow I've shown underneath the three examples shows an increasing trend of, or an increasing rate of hydrolysis. Okay, so we can annotate that red arrow. So we've got increasing rate of hydrolysis. Okay, and I suppose the question is, why should that be the case? Why should it be that when you change from a chlorine bonded to a carbon to a bromine bonded to a carbon, you should be able to hydrolyze that carbon-bromine bond much more easily? Why should it be the case that you are able to hydrolyze the carbon-iodine bond a lot more easily than the carbon-bromine bond? Well, it all comes down to the bond enthalpy, so the bond energy, how much energy is required to break that carbon-halogen bond. And it turns out that as you go down the group, as you go from chlorine to bromine to iodine, the bond energy or the bond enthalpy is reduced. Okay, so we should make that point here. So we've got lower bond enthalpy as the halogen gets bigger. Okay, so you've got a lower bond enthalpy, which means that it is easier to break. Less energy is required to break the carbon-halogen bond. So less energy for the carbon-iodine bond compared to the carbon-bromine bond, which in turn requires less energy than the carbon-chlorine bond. Okay, so if you think about it a bit more deeply, as you increase the size of the halogen atom, you've got a greater distance between the bonding pair in the middle of that bond and the respective nuclei, and you've got a weaker attraction. Okay, so you've got a weaker force of attraction between the two atoms, either so between the pair of electrons and the two nuclei either side. So you've got a weaker bond. Okay, so and there is a very handy experiment that you can do to show the difference in the rate of hydrolysis. This is something you're required to be able to recall, and this is where you hydrolyze your halogenoalkane or your carbon halogen bond using water, but in the presence of silver nitrate. If you think back to your GCSE chemistry days, you'd have made sort of precipitates of various silver halides, and this is exactly what you're doing in this hydrolysis. So if you've got water present, the water has to be dissolved in ethanol so that you've got your halogenoalkane also sort of dissolved in the mixture. The one thing we haven't mentioned yet is that halogenoalkanes are not very soluble in aqueous media, and so you need the presence of ethanol for this reaction to work. So if I highlight that for you, so we've got ethanol here, and if I annotate that to make it a bit clearer, so ethanol needed as solvent. Okay, why? Because the halogenoalkane would not dissolve in water otherwise. So you've got ethanol as solvent, and you've got some water present, and you're going to warm this mixture. And well, you don't necessarily need to warm it, but in the presence of your silver nitrate, once the carbon halogen bond has been broken, you're going to end up forming a silver salt. So in this instance, if it were chloroethane you were hydrolyzing, then you would end up forming a silver chloride salt. So the AgX that I've shown in my equation here, highlighted here, would be a silver salt, and an example of that would be silver chloride, for instance, which is a white precipitate. Okay, so you're going to measure how quickly it takes to make the precipitate of the silver salt. And of course, if you were to compare a chloroalkane, a bromoalkane, and an iodoalkane, you should find that the formation of the silver iodide precipitate happens a lot faster. And silver iodide, of course, is also sort of a yellow sort of color, quite distinct from the white of silver chloride and the cream of silver bromide. So it's formed a lot faster and it's very distinct. If you were trying to tell apart your silver chloride and silver bromide, they are formed, silver chloride should be formed much faster than your silver bromide precipitate. Okay, so to go over that particular experiment again, you're going to have your halogenoalkane dissolved in ethanol and water, but also with silver nitrate present. And as soon as you start that reaction by sort of adding your halogenoalkane to the water ethanol mixture, your precipitation should occur, your silver halide should form, and how quickly that forms tells you how easily the carbon halogen bond is broken. Okay, so let's make a point of writing that as well. So the rate of forming your silver halide precipitate, so solid, tells you how quickly our carbon halogen bond is broken. Okay, so something to bear in mind as far as your practical chemistry is concerned. Okay, so that's hydrolysis, but let's look at it in terms of the mechanism. What's actually going on when water breaks that carbon halogen bond, or even in the instance where you use aqueous alkali as your nucleophile. Okay, so we've got two examples here. We've got sodium hydroxide, aqueous sodium hydroxide, reacting with chloroethane. And of course, in this instance, you've got the hydroxide ion as your nucleophile. And of course, you've got a lone pair on that oxygen. Now, you've got a polar carbon chlorine bond. So you've got a delta plus on your carbon and a delta minus on the chlorine. And as far as the mechanism goes, the lone pair on the hydroxide ion is going to attack the delta plus of your carbon chlorine bond. So if I draw that as such, and at the same time, you're going to get the breaking of your carbon chlorine bond. Now, the pair of electrons in that carbon chlorine bond are going to be repelled by the incoming pair of electrons from the hydroxide oxygen. And so that causes this second arrow, the second movement of a pair of electrons. And what you end up with is, of course, the formation of your alcohol. So if I draw that in blue, and let's stick to our color coding. So there's your OH that's just been added, and we've also made a chloride species, so Cl minus, and because you've got sodium ions present, you're going to end up forming sodium chloride as the other product. Of course, sodium chloride is soluble, and so you're not going to see it, so it's all going to be dissolved in your solvent. In this case, we've got aqueous sodium hydroxide, so your sodium chloride form will be dissolved in the water. That is the solvent. Okay, so this is an example of a nucleophilic substitution mechanism, and we can label this as such. So our nucleophile is our hydroxide ion, and it has replaced the chlorine atom, and it has kicked out a chloride ion as our product. Okay, so nucleophilic substitution, if we highlight the nucleophile, okay, our electron pair donor is the hydroxide ion, and we can label that as a nucleophile. Okay, that's our electron pair donor, and it replaces the chlorine in your halogenoalkane, and so it is a substitution reaction. Okay, so we've got hydrolysis in aqueous alkali. What we can also look at is hydrolysis by water. So this would be in the example where I described on the previous slide, where we were looking at hydrolysis in the presence of silver nitrate. So this is what the water molecule is doing. Now, the water molecule is, of course, uncharged, unlike your hydroxide ion, but it is still an effective nucleophile. Why is it an effective nucleophile? It's got lone pairs on the oxygen. Either one of those lone pairs is your electron pair that will be donated. Okay, and so just as we saw before, you've got a delta plus on that carbon shown there, and a delta minus on that chlorine, and the curly arrow is going to start from the lone pair. Remember, curly arrows have to start from a pair of electrons, so lone pair on the oxygen of water, and it's going to end up at that carbon with a delta plus. And then, as usual, the C-Cl bond is going to break because the incoming electrons are going to repel the bonding pair of electrons in that bond and cause that bond to break, so that you now have a chloride ion as a byproduct. So if we draw the result of those two curly arrows, we now have a bond between the oxygen of water. The water still has two hydrogens. We've got a plus charge on the oxygen this time. You can think of the oxygen of the water as being electron deficient now, because it's having to form a dated covalent bond to that carbon that it's just attacked, and so it will be electron deficient, and so we'll have a plus charge on it. Whenever you've got an oxygen with 3 bonds on it, automatically think plus charge on the oxygen. Now, of course, the other product formed is our chloride ion, and if we show that, so Cl minus. Now, if you pay close attention to what's going on in terms of charges, you'll see that the water molecule is neutral, your halogenoalkane is neutral, and in the intermediate step, or rather for the intermediate products, you've got a plus charge on your oxygen of the intermediate, the organic intermediate, but that is cancelled out by the minus charge on the chloride ion. So again, charge is always conserved. So always make sure that you're checking that you've got the same charge on the left-hand side of any arrow as you've got on the right-hand side. Okay, so the final step leading to our alcohol is, of course, the loss of our proton from that intermediate. And to show that, if we keep to our black curly arrows, either of these oxygen-hydrogen bonds will be broken. Okay, so when that happens, you're going to be left with an H plus ion and your OH. And of course, that H plus ion is going to pair up with your chloride ion to give you HCl. So again, you've got a nucleophilic substitution mechanism. And if we sort of make that point clearer, so you've got a nucleophilic substitution mechanism for both of these. The difference between the two is that if you have a neutral nucleophile, then you will have a second step where you've got a positively charged intermediate, which then has to be, so that positive charge then has to be quenched. So if I highlight the intermediate in question here. So because we've got a neutral nucleophile, we're going to end up with an intermediate that has a positive charge on it. Okay, so if you were carrying out this nucleophilic attack using, say, ammonia, which I'll show you on the next slide, you would form a positively charged intermediate. Okay, so these are two examples of the nucleophilic substitution mechanism. Right, now at this stage, I will have a quick look in my chat box to see if there are any questions. There doesn't seem to be any, so we will carry on with our work. We'll look at some more examples of nucleophilic substitution. We'll look at some nucleophiles that you will encounter and sort of talk about in a bit more detail at A2. At this stage, I'll just show you how they are nucleophiles, and we'll repeat the mechanism that you've just seen on our screen. So we're looking at ammonia as a nucleophile, and of course the reason ammonia is a nucleophile is because it has a lone pair on the nitrogen of our ammonia molecule. Okay, so if we highlight that lone pair there, that's what's going to be used in the nucleophilic attack. And just as you saw before, you've got a curly arrow going from our lone pair to the carbon, which will have a delta plus charge on it. I haven't shown the dipole here, but by this stage you should all be able to recognize why that carbon is attacked. Your bromine is more electronegative than that carbon atom, so that bond is polar. Okay, so as a result of that curly arrow to that carbon atom, we're going to break the CBr bond, as shown, and because we've got a neutral nucleophile in our ammonia, you're going to end up with an intermediate that has a positive charge. So in this instance, you've got an ethyl ammonium salt. Sort of losing my color coding a bit. That's fine. We draw in all the bonds to the hydrogens there. A plus charge on the ammonium species, and of course we will have made a bromide ion as a result. Okay, so and then this is something you will look at again at A2, but in quenching or getting rid of that plus charge on your ammonium intermediate, another molecule of ammonia would typically come in, acting as a base, and remove one of those protons. I'm not going to show you what I suppose I could show you it. So if we have our second molecule of ammonia coming in, the lone pair on the nitrogen, of course, to that hydrogen, and then onto our nitrogen atom. And that explains why in the balanced equation, in the overall equation, you've got 2 moles of ammonia, so that you form the amine, and you then also form ammonium bromide as your other product. Okay, so if I highlight that fact, you've got 2 moles of ammonia in your overall equation, and the reason for that is because you need 1 mole of ammonia to attack your carbon with a delta plus, and a second mole of ammonia here to remove a proton from the intermediate. Okay, so something you'll come back to in the second year of A level. For now, just treat ammonia as another nucleophile, a bit like water. It's neutral. It attacks your carbon of your CBr bond and forms a positively charged intermediate. And you can show the removal of the proton in that positively charged intermediate by simply sort of drawing a curly arrow from the NH bond to the nitrogen. So in fact, what you can do in your first year, yes, is to simply show it as that. Okay, so that's another way of showing that second part of the mechanism. And then very quickly, we can look at the cyanide ion as a nucleophile. So if you react your bromoethane with sodium cyanide in ethanol, which would be our solvent, you've got your cyanide species, which is CN, and you've got a minus charge on that carbon there, and there is a lone pair on the carbon. So unlike with sort of the ammonia nucleophile and sort of amines, in your cyanide ion, you've got a lone pair on the carbon atom that is the nucleophilic lone pair rather than the lone pair on the nitrogen. Again, you can discuss this at length in the second year. For now, same as before, you've got a curly arrow. You're going to go red this time. We're going to use a curly arrow from the lone pair on your carbon atom to the carbon of your CVR bond, and then breaking the CVR bond. And if we, for completion sake, put delta plus and delta minus across that bond. Okay, so this time round we've got a nucleophile that is negatively charged. So in your products, you're going to have a neutral product. So you're going to have a nitron. So we've got a carbon, and there we go, so CN. So what this does is also extend the carbon backbone of your organic molecules. So we now have 3 carbon atoms, something that you will look at in a bit more detail in the second year. And of course, you're going to be forming a bromide ion as your inorganic product. Okay, so again, 2 more examples of the nucleophilic substitution mechanism. You've got your nucleophiles highlighted in yellow, so your ammonia and your cyanide ion, and they both attack the delta plus of your carbon halogen bond. You've got a delta plus on the carbon atom because your halogen is more electronegative and pulls electron density in that covalent bond towards itself, leaving your carbon atom electron deficient. Okay, so some more examples of nucleophilic substitution there for you. Okay, so at this stage, another quick check to see if there are any questions. There aren't, so we will move on to look at another aspect of halogenoalkanes that you're required to know about in your first year, and this is to do with the fact that under certain conditions, you can end up producing halogen radicals. Halogen radicals are very reactive species which have unpaired electrons. So a radical is a species with an unpaired electron, and these are critical to disrupting, or play a crucial role in disrupting the amount of ozone we've got in the upper atmosphere, which isn't a good thing. Ozone, of course, blocks out harmful UV rays. And how does this happen? So if you've got UV present and you've got a chlorofluorocarbon, such as the one shown here, so we've got dichloro. Remember, it's named in alphabetical order. So we've got dichloro-difluoromethane. If you've got UV present, which of course you'll have lots of in the upper atmosphere, you can end up breaking the carbon-chlorine bond, and that would leave you with a chlorine radical. And if you did this, so this bond breaking process here is homolytic, of course. We've got a homolytic fission of the carbon-chlorine bond, and that can leave you with a CF2 Cl radical and another chlorine radical there. Okay, so the species we want to pay attention to is the chlorine radical that we've just formed, because it will act as the catalyst for the depletion of ozone in the upper atmosphere. So in the next equation that I've got half written, your chlorine radical is going to be reacting with ozone. Ozone is this O3 molecule shown here. We label that as ozone. It's going to react with the chlorine radical, and in doing so, it will lead to the formation of oxygen and also a chlorate radical, so ClO dot. Okay, so that radical can then go on to react with oxygen atoms to reform chlorine radicals, and the cycle continues over and over again. You keep forming chlorine radicals and more oxygen. And it's obviously something that needs to be addressed. And of course, over the years, the use of chlorofluorocarbons, such as the one we've got here, has been banned, and that has gone some way towards sort of, fixing or sort of helping the ozone layer to recover. Okay, so if we finish our equations, if we react our chlorate radical with the oxygen atom, you're going to end up reforming your chlorine radical and an oxygen molecule. Okay, so that chlorine radical that you've just reformed, so it gets used up initially, breaking up ozone, and then gets reformed when the chlorate radical reacts with an oxygen atom. That chlorine radical is now available to go back and react with some more ozone. Okay, so that is something that is sort of environmentally sort of very important, something you need to obviously know the chemistry of as well. Okay, so that is the formation of halogen radicals from halogenoalkanes. I think the next thing to do is to look at some practice exam questions. And in today's session, we're going to be looking at AS paper 2. We're going to look at the 2017 paper and questions 5D and question 6A part I. And we'll also look at paper 2 from 2018 and question 5A part I. Okay, so I have shared both papers with you in the chat box if you want to open the papers. There is a data booklet in the chat box as well. So let's look at the first one then. So the 2017 paper, and we're looking at question. This is 5D, I believe. Yep, it is 5D. And we're looking at 2-chloropropanoic acid, and we're told that it can be made by reacting propanoic acid with chlorine in a radical substitution reaction. Okay, so state the conditions for the reaction. This is a bit of practice at the radical mechanism that we've just seen for sort of in ozone depletion. And the same applies to this question. So in order to form our radical species, you would need to, of course, have UV present to give you the chlorine radical. And we're asked to write the overall equation for the reaction. So the overall equation involves propanoic acid, which is CH3, CH2, C double bond OH. So that's our propanoic acid. And this is reacting with chlorine, and we're reacting the two in the presence of UV. Okay, so that would give us our chlorine radical. And in this reaction, you end up forming our 2-chloropropanoic acid. So we've got CHCl and C double bond OH as our product. I have left out an L, there we go, CHCl. And then you're going to form HCl as your inorganic product. Okay, so the overall equation sees a chlorine radical reacting with your propanoic acid, and it forms your HCl and eventually your 2-chloropropanoic acid. Okay, so the first step in the reaction mechanism involves homolytic fission of the chlorine molecule to form 2 chlorine radicals. Why is this step an example of homolytic fission? Both chlorine atoms, both Cl atoms in Cl2 receive one of the bonding electrons when the Cl-Cl bond breaks. Okay, so in homolytic fission, the electron pair in the covalent bond is split evenly between the 2 atoms either side of the covalent bond. So if you've got Cl2, which is of course Cl, the bonding pair between that Cl and another Cl, then the 2 electrons of the bonding pair, one of those electrons goes to one chlorine atom, and the other goes to the other chlorine atom. Okay, And in the next part, we're asked to write two equations to show the propagation steps in the mechanism for this reaction. And we're asked to use dots to show the unpaired electrons on radicals. Okay, so in the propagation step, you've got your propanoic acid, CH3, CH2, C double bond OH, and that is reacting with the chlorine radical. Okay, so in all propagation steps, you've got a radical species and a non-radical species, and in this reaction, or in this step, you will end up forming this CH3, CH, and COOH radical. We can put the radical, we can put the dot on that carbon. It can appear anywhere on this intermediate, and of course HCl. And in the second propagation step, you've got your CH3, CH radical, COOH radical, reacting with the chlorine molecule. So chlorine molecule is our non-radical species, and that leaves us with the product CH3, CHCl, C double bond OH, and another chlorine radical. Okay, so those are the two equations we need to write, and we're then asked to draw the displayed formula of the radical formed in the first propagation step. So if I rewrite that or redraw that, remember it's a displayed formula, so all bonds to atoms must be shown, and we've got C double bond O, and we've got OH. Okay, so that would be our radical intermediate from the first propagation step formed. And finally, we're told that further substitution forms a mixture of organic products. Draw the structure of an organic product formed from 2-chloropropanoic acid by further substitution. There are any number of possibilities. Each of the hydrogens in our 2-chloropropanoic acid can be substituted further, so we could go on to have the CH2Cl, CHCl, COOH as another possible product, but there are any number that you could draw. Okay, so that's that question out of the way. If there are any questions, do please use the chat box. We'll consider the next question. This time round, we're told that a student devises a two-stage synthesis of cyclohexene from bromocyclohexane, and in part one, we're asked to suggest the structure of intermediate E and the reagents and conditions for step 2. I guess our main focus here is intermediate E, because that is relevant to the work we've just been doing. It should happen via a nucleophilic substitution mechanism. So in this instance, the OH minus from sodium hydroxide, aqueous sodium hydroxide, is going to be our nucleophile. And if we draw the intermediate, and of course I will take this opportunity to go through the mechanism. We're not asked for it, but I will show you just the same. So we're starting with our or bromocyclohexane, I should call it, if I draw it there. And we've got sodium hydroxide, and so you've got OH minus ions, aqueous sodium hydroxide. Of course, you've got a delta plus on that carbon and a delta minus on the bromine, and so you're going to have a curly arrow from lone pair to that carbon atom. Perhaps let's show the arrowhead properly, ending at the correct spot. There we go. And you've got that electron deficient carbon with the delta plus being attacked by the lone pair of the hydroxide ion, and the bonding pair in the CBr bond are of course repelled onto the bromine atom, and you're going to end up with your intermediate. Your intermediate is of course your cyclohexanol. We draw that there. So that is intermediate E shown there, and we've gone a bit further than we were required to, but it's useful to practice drawing the mechanism. And of course the other product which we're not required to show would be your bromide ion. Okay, so we've got the intermediate E shown there. Now, this is not sort of relevant to what we've been discussing, but if you wanted to go from your cyclohexanol to your cyclohexene, then you could react that, you could dehydrate that cyclohexanol by using concentrated phosphoric acid, for instance, to furnish you with the alkene. Okay, so your phosphoric acid is sort of what you would need as H3PO4 to go back to the cyclohexene molecule. Okay, so those are, I believe, all of the questions on the 2017 paper we want to look at. There's one final question I'd like us to look at in the 2018 paper. So this is Depth in Chemistry, paper 2, AS, and we're looking at question 5A, so 5A of the 2018 paper. Okay, and this is one that sort of looks at a bit of practical chemistry. We're told in 5A that 1-bromobutane is an organic liquid with a boiling point of 102 degrees Celsius. A student prepares 1-bromobutane by reacting it with butanol and sulfuric acid, or sorry, prepares 1-bromobutane by reacting butanol with sulfuric acid and sodium bromide. Okay, so the sulfuric acid and sodium bromide will furnish bromide ions, which can then react with your alcohol and substitute the hydroxide, or rather the OH group present, to give you water. Okay, so the student obtains a reaction mixture containing an organic layer. Okay, so the organic layer will be our halogenoalkane. Of course, the halogenoalkane is denser than water, and so it will be the bottom layer, and your water will be the top layer, or the aqueous layer will be the top layer. Okay, so we're asked to draw a label diagram to show how you would safely set up the apparatus for the preparation. Now, in this question, there are sort of two parts to your answer. You need to be talking about the preparation of the halogenoalkane, and then in the second part, to outline a method to obtain a pure sample of 1-bromobutane from the reaction mixture. Okay, so method to obtain a pure sample from of 1-bromobutane from the reaction mixture. Okay, so draw a label diagram to show how you would safely set up the apparatus for the preparation of the halogenoalkane. Well, in this instance, you're going to require a reflux. So you're going to have a round bottom flask or a pear-shaped flask, doesn't matter. You're going to insert a condenser via a quick fit joint, and if we there's our condenser, if we complete the drawing of our condenser to show the water inlet and the water outlet. Okay, so labeling, always annotating your diagram, so that's your condenser, and saying the water goes in at the bottom, the water in, and water out at the top. Okay, so remember this is a reflux, and we need to ensure that we're condensing the vapors from the reaction mixture back into our flask. We're going to be heating that flask using a heating mantle. So heating mantle, and of course in our flask you're going to have a mixture of your in this case your butanol. So if we label that, so butanol, and you're going to have some anti-bumping granules. You're going to have some sulfuric acid and sodium bromide in there as well. And some sodium bromide. Okay. Okay, so that's what your reaction mixture is. And once you've refluxed this for sort of long enough, you should form your halogenoalkane, and you will see that you will have 2 layers in your reaction mixture. How are you going to separate out the halogenoalkane from the aqueous mixture? So this is the reflux stage, if we label that as such. So reflux, and highlight that to make it stand out. Okay, we now need to separate out our halogenoalkane, and because it's of a higher density, it's going to be you're going to have 2 layers, and you're going to need to use a separating funnel. If I draw a separating funnel here, so separation, and again highlighting it. And if we draw a separating funnel, we're going to okay, that's the tap on my separating funnel. And if we look at the 2 layers in there, and if we label that, and if we label the top aqueous and the bottom halogenoalkane. Okay, so you're going to open the tap and drain out the halogenoalkane, and then from that you're going to dry your halogenoalkane using anhydrous magnesium sulfate would be a good example. Okay, so anhydrous magnesium sulfate to dry your halogenoalkane to get rid of any sort of water that might be in the organic layer. And then having dried it, you'd need to filter it. So the filter under gravity should be enough, and you should then have a your haloalkane. And if you want to go a step further, you can then sort of redistill it and have your pure haloalkane. Okay, so this is a very quick sketch of what you would need to do to get full marks on this particular question. So identifying that there are 2 parts to it. So drawing a label diagram to show how you would safely set up the apparatus for preparation. Note that we're using a heating mantle and not a Bunsen burner, because your alcohol is likely to be flammable. So heating mantle, reflux condenser, and then when you form your halogenoalkane, it then becomes a case of how do you separate it from the aqueous layer. You need to use a separated funnel because the halogenoalkane is denser, and so you can separate it out that way. You can dry the halogenoalkane, which is a liquid. We're going to dry it by using a drying agent like anhydrous magnesium sulfate, and then filter out the magnesium sulfate, and the liquid you've got, you can then redistill it to get rid of any other sort of liquid impurities. Okay, so that's a very good question to test your practical knowledge of, in this case, halogenoalkanes. Okay, so that brings us to the end of this evening's session. I hope it's been worth the wait for you. Apologies once again for the technical issues we had yesterday. And as usual, my message to you is to go away, sort of rewatch what we've just done, and find some more practice questions to tackle on halogenoalkanes and the nucleophilic substitution mechanism in particular. The only way to master mechanisms is to draw out mechanisms and check against a mark scheme, for example, or your checklist for ensuring you're applying principles for using curly arrows correctly. Okay, so I'm going to have to say goodbye. It's been a pleasure as usual, and I look forward to seeing you again next Sunday for our next session. Thank you very much for joining me, and have a good evening.